Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on gases, and we've made it to the fourth objective. The fourth objective deals with gas stoichiometry, and here we want to start by revisiting Avogadro's law. Avogadro's law states that when the temperature and pressure remain constant, the volume of a gas is directly proportional to the number of moles of gas. Now, there are two important consequences of Avogadro's law. First, when we're solving gas stoichiometry problems, if all of the gases are measured at the same temperature and at the same pressure, then instead of using mole-to-mole ratios, we can use liter-to-liter ratios. So, for example, take this reaction between nitrogen gas and hydrogen gas. We can say that 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to form 2 moles of ammonia. However, because of Avogadro's law, we can equally say that we have 1 liter of nitrogen gas reacting with 3 liters of hydrogen gas to form 2 liters of ammonia. And so we can use liter-to-liter ratios in a very similar way to how we use mole-to-mole ratios. And this is a very useful relationship. However, there are 2 important caveats. First, we can only use liter-to-liter ratios for gases, not for liquids and not for solids. Second, we can only use liter-to-liter ratios for 2 gases if they are both measured at the same temperature and at the same pressure. The second important consequence of Avogadro's law is that the molar volume of any gas at STP is 22.4 liters. STP stands for standard temperature and pressure, and that is equal to 273 Kelvin and 1 atmosphere. Now, molar means pertaining to 1 mole. So just as molar mass means the mass of 1 mole, molar volume means the volume of 1 mole. So in other words, the volume of 1 mole of any gas at 273 Kelvin and 1 atmosphere is 22.4 liters. And this gives us these 2 important conversion factors. Now, you must be careful when you apply these conversion factors. All right, keep in mind that 22.4 liters per mole only applies to gases. Again, not for liquids and not for solids. In addition, 22.4 liters per mole only applies when a gas is measured at 273 Kelvin and 1 atmosphere. So that is our fourth objective. Let's go ahead and move into our fifth objective, which focuses on Dalton's law of partial pressure. When 2 or more gases that do not chemically interact are found in one vessel, each gas will behave independently of the others. That is, each gas will behave as if it were the only gas in the container. Therefore, the pressure exerted by each gas in that mixture is going to be equal to the pressure that that gas would exert if it were just the only gas in the container. The pressure that is exerted by each individual gas, that has a name. It's called the partial pressure of that gas. And in 1801, John Dalton derived an expression that we now know as Dalton's law of partial pressures, which states that the total pressure of a gaseous mixture is equal to the sum of the partial pressures of the individual components. Let me reiterate. The total pressure of a gaseous mixture is equal to the sum of the partial pressures of the individual components. So that equation is shown here for Dalton's law. PT, this is the total pressure in the container. PA is the partial pressure of gas A. PB is the partial pressure of gas B, and so on and so forth. And again, when more than one gas is in a container, each contributes to the whole as if it were the only gas present. If you add up all of the pressures of the individual gases, you get the total pressure of the system. Now, The partial pressure of a gas, let's take gas A for example, the partial pressure of gas A is going to be related to the mole fraction of gas A multiplied by the total pressure of the system. Now, what is mole fraction, you might ask? Mole fraction is defined for, let's say, gas A as the moles of gas A divided by the total moles of gas in your container or in your system. So to summarize, in a mixture of gases, each component behaves as if it were the only gas in the container. And that's because gas molecules are very far apart and they do not affect each other greatly. Each component gas contributes, though, to the overall pressure of the gas mixture. Wonderful. Let's take these equations, apply it to a practice problem that we're going to do together. This example reads, a vessel contains 0.75 moles of nitrogen gas, 0.2 moles of hydrogen gas, and 0.05 moles of fluorine gas at a total pressure of 2.5 atmospheres. What is the pressure of each gas? Let's start off by writing down all of our equations that we know. We'll start off with writing Dalton's law of partial pressures. This states that the total pressure of a gaseous mixture is equal to the sum of the partial pressures of the individual components. So the total pressure is going to be equal to the partial pressure of nitrogen gas plus the partial pressure of hydrogen gas plus the partial pressure of fluorine gas. Now, what we're trying to figure out is the pressure of each gas. Do we have an expression that can help us calculate the partial pressure of each of these gases? The answer is yes. If we want to figure out the partial pressure of nitrogen gas, that's going to be equal to the mole fraction of nitrogen gas multiplied by the total pressure. If we want to figure out the partial pressure for hydrogen gas, this is equal to the mole fraction of hydrogen gas multiplied by the total pressure. And the same goes for fluorine gas. This is going to equal the mole fraction of fluorine gas multiplied by the total pressure. Now, how do we figure out the mole fraction for each of these gases? Well, the mole fraction for nitrogen gas is just going to be the moles of nitrogen gas over the total moles. What about for hydrogen gas? It's going to be moles of hydrogen gas over total moles. And the same goes for fluorine gas. The mole fraction of fluorine gas is going to be the moles of fluorine divided by the total moles. Now, looking at these set of equations, what information do we have? We have the total pressure. The total pressure is equal to 2.5 atmosphere. And we also have the moles of each of these gases. We have the moles for nitrogen gas, hydrogen gas, and fluorine gas. So we have the numerator for each of these expressions. We can also easily figure out the denominator. The denominator is the total number of moles in your system. To figure that out, we just have to sum the moles of hydrogen gas plus nitrogen gas plus fluorine gas. That's going to be 0.75 plus 0.20 plus 0.05. That gives us a total of 1. Our total moles in this system is 1 mole of gas. So now we have our total pressure, we know the number of moles for each of our gases, and we know the total number of moles in this system. Let's go ahead and calculate first the mole fraction for each of our gases, and then we're going to go ahead and plug them into our equations here to get the pressure for each gas. Now, the mole fraction for nitrogen gas is going to be 0.75 moles divided by 1, and that gives us an answer of 0.75. For hydrogen, it's going to be 0.20 moles over 1, and that gives us an answer of 0.20. And then for fluorine gas, it's 0.05 divided by 1, and that gives us 0.05. Now we can go ahead and plug them into our equations for the partial pressure. The partial pressure of nitrogen gas is going to be 0.75 multiplied by the total pressure, which is 2.5 atmosphere. This gives us an answer of 1.875 atmosphere. So the partial pressure for nitrogen gas is going to be 1.875 atmosphere. What about for hydrogen gas? This is going to be 0.2 multiplied by 2.5, and that gives us an answer of 0.5 atmosphere. The partial pressure for hydrogen gas is 0.5 atmosphere. And then for fluorine, we're going to multiply 0.05 by 2.5, and that gives us the partial pressure for fluorine gas. The partial pressure for fluorine gas is 0.125 atmosphere. And there we have it. We have solved this problem. We've determined the partial pressure for each gas. Wonderful. Let's move on to our next topic. This next topic is focused on Henry's law. Now, the difference in gas solubility between fluids was explained by William Henry in 1803. What Henry noticed was that at various applied pressures, the concentration of a gas in a liquid increased or decreased. This was a characteristic of a gas's vapor pressure. Vapor pressure is the pressure that's exerted by evaporated particles above the surface of a liquid. Now, evaporation is a very dynamic process that requires the molecules at the surface of a liquid to gain enough energy to escape into the gas phase. Vapor pressure then from the evaporated molecules forces some of the gas back into the liquid phase, and equilibrium is then reached between evaporation and condensation. Now, mathematically, this process is expressed by the following equations. Here we have the concentration of A in solution. This is equal to Kh, which is Henry's constant, multiplied by the partial pressure of A. Now, something to note is that the value of Henry's constant depends on the identity of the gas. So the best way to understand this is to do a practice problem. But I also want to introduce this kind of expression in a different form. You see that right here. Here we have the concentration of gas A at some initial value divided by initial pressure. This is equal to the concentration of that gas at some final value divided by final pressure. And this is also equal to Henry's constant. Let's go ahead and read this problem and see how we can tackle it based off of what we just learned about Henry's law. This example says, if 4 times 10 to the minus 4 moles of gas are dissolved in 2 liters of a solution under an ambient pressure of 2 atmosphere, what will be the molar concentration of that gas under 10 atmosphere? Now, what we have here is some initial pressure and some final pressure. We're also given just enough information to calculate the initial concentration of this gas. And that means that we can go ahead and use the following expression to figure out what the final molar concentration of this gas is going to be after the pressure is changed from 2 atmosphere to 10 atmosphere. We're going to use this expression that I am writing out right now. Let's go ahead and calculate this initial concentration. This is going to be equal to moles divided by liter. Moles is 4 times 10 to the minus 4, and we are given a volume of 2 liters. This gives us a molarity of 2 times 10 to the minus 4. Now we know 3 out of the 4 variables, so we can easily rearrange this expression to solve for final concentration. Final concentration is going to be equal to initial concentration multiplied by final pressure divided by initial pressure. This is going to be equal to 2 times 10 to the minus 4 molar multiplied by 10 atmosphere divided by 2 atmosphere. Now we can cancel out the 2's that appear in both the numerator and denominator, and we essentially just have 10 to the minus 4 multiplied by 10. This gives us a final concentration of 10 to the minus 3 molar. So the molar concentration of the gas under 10 atmosphere is going to be equal to 10 to the minus 3 molar. Wonderful. With that, we've completed the 5th objective, and now we can move into our 6th objective, which is focused on the kinetic molecular theory. The kinetic molecular theory of gases shows how the macroscopic properties of gases result from the behavior of the individual particles making up the gas. Let's go ahead and go over the postulates for this theory. The first point that we want to make is that gases consist of individual molecules or atoms in constant random motion. And these gas molecules, they can collide with each other, and they can also collide with the walls of the container. Pressure actually results from the forces associated with the collision of the gas molecules with the walls of the container. The second postulate is that gas molecules are extremely small compared to the distances between them. This means that most of the volume occupied by a gas is actually empty space. The third postulate states that collisions between gas molecules are elastic. This is another way of saying that when gas molecules collide, there is no loss of energy because elastic collisions are ones in which the total kinetic energy before and after a collision remains the same. The fourth postulate states that attractions between gas molecules are extremely weak and negligible. We can also say that gas atoms or molecules exhibit no intermolecular attractions or repulsions. And finally, the last postulate states that the average kinetic energy of gas molecules depend only on temperature. They do not depend on pressure, volume, not even the identity of a gas, only on temperature. And this actually is going to help us transition into a very important point. According to the kinetic molecular theory of gases, the average kinetic energy of a gas particle is proportional to the absolute temperature of the gas. And we can see that in the following equation. Here we see that kinetic energy is equal to 1/2 mv squared, where m is mass and v is velocity. Kinetic energy is also equal to 3/2 kb multiplied by T, where T is temperature, and kb is the Boltzmann constant. This is equal to 1.38 times 10 to the minus 23 joules per Kelvin. Now, this relationship serves as a bridge between the macroscopic and the microscopic behaviors of gases. So this is a bridge between the behavior of the gas as a whole and the individual gas molecules. This equation essentially shows that the speed of a gas particle is related to its absolute temperature. However, because of the large number of rapidly and randomly moving gas particles, the speed of an individual gas molecule is nearly impossible to define. Therefore, the speeds of gases are defined in terms of their average molecular speed. And one way to define an average speed is to determine the average kinetic energy per particle and then calculate the speed to which this corresponds. The resultant quantity, known as the root mean square speed, is given by the following equation. It is equal to the square root of 3RT divided by m. R here is the ideal gas constant, T is the temperature, and m is the molar mass. Now, related to this, we can look at the following relationship. This is a Maxwell-Boltzmann distribution curve. These curves show the distribution of gas particle speeds at a given temperature. And here we show a distribution curve of molecular speeds at two temperatures, T1 and T2, where T2 is greater than T1. Notice that the bell-shaped curve flattens and shifts to the right as the temperature increases, indicating that at higher temperatures, more molecules are moving at higher speeds. Let's go ahead and take all of this information that we've learned and apply it to this example problem here. This example says, what is the average speed of xenon difluoride molecules at 20 degrees Celsius? Now, for this problem, we're going to be using our root mean square speed equation. So let's go ahead and write that down. That's going to be equal to the square root of 3RT divided by M. Now, this example is a really good opportunity to discuss what units for each of these variables we should use. Let's start off with our ideal gas constant. We want to use the ideal gas constant that has units of joules per Kelvin times mole, and this is because things will cancel out appropriately so that we get our final answer in meters per second. The value of the ideal gas constant is going to be 8.314 joules per Kelvin times mole. Now for temperature should be in Kelvin, but we're given 20 degrees Celsius, so we can convert that to Kelvin by adding 273, and we get 293 Kelvin. Now, the last variable is molar mass, and the molar mass of xenon difluoride is 169.3 grams per mole. But here, molar mass has to be expressed in kilograms per mole because joules are also derived from kilograms, and we want those units to cancel out appropriately. So the molar mass that we're going to write here for xenon difluoride is 0.17. We're approximating 169 here to 170 and then dividing by 1,000 to get 0.17 kilograms per mole. Now let's go ahead and plug things back into our expression and start approximating numbers so that our calculation is easy without using a calculator. What we're going to get is the square root of 3 multiplied by 8.314 joules per Kelvin times mole multiplied by temperature, which is 293 Kelvin, and that's going to be divided by our molar mass, which is 0.17 kilograms per mole. Now, let's go ahead and approximate some of these numbers, and let's try to approximate numbers so things can cancel out appropriately. So I'm going to approximate 8.314 to just 8, and I'm going to approximate the temperature to 300 Kelvin, and then I'm going to approximate the molar mass to about 0.18. This is really close to 0.17, but 0.18 is divisible, 18 is divisible by 3, so that's going to make that kind of calculation a lot easier for us, because now I can cancel out the 3, all right, divide the numerator and the denominator by 3, and what we get left with is 8 times 300 over 0.06, and this is all under the square root. Now, what else is really easy is this calculation right here. 300 divided by 0.06, this is equal to 5,000. So now we have square root of 8 multiplied by 5,000. 8 times 5,000 is 40,000, and the square root of 40,000 is going to be just 200, because 200 squared is going to give us 4,000. So our average speed for the xenon difluoride at 20 degrees Celsius is approximately 200 meters per second. Now, if you go ahead and plug in the real values into a calculator, you'll get something along the lines of 208 meters per second, which is really close to the value we approximated. Wonderful. Let's move on to our next objective. In the study of gases, two phenomena that illustrate the behavior of gas molecules are diffusion and effusion, both of which are closely related to the principles of kinetic molecular theory. Now, diffusion is the process by which molecules spread from an area of high concentration to an area of lower concentration. It is the spontaneous mixing of substances due to the random motion of their particles. In the context of gases, this means that gas molecules spread out until they are evenly distributed throughout the available space. Effusion, on the other hand, refers to the movement of gas particles through a tiny opening into an evacuated space or vacuum. Now, this occurs because the molecules are in constant random motion and some will eventually hit the opening and pass through it. The rate at which this happens depends on the velocity of the gas molecules, and that is also affected by their mass. Now, from there, we want to move into discussing Graham's law of effusion mathematically. All right, and mathematically, it relates the rates of effusion for two different gases to their molar masses. It tells us that the rate of effusion of a gas is inversely proportional to the square root of its molar mass. Now, this can be represented by this equation that we see here. R1 over R2 is equal to the square root molar mass 2 over molar mass 1. Now, R1 and R2 are the effusion rates of the two gases. M1 and M2 are their respective molar masses. In essence, lighter gases with lower molar masses effuse more rapidly than heavier gases because their molecules on average move faster. Now, this principle also extends to diffusion, as lighter gases will diffuse more quickly due to their higher velocities. Therefore, the molecular speed, which is a function of the molar mass of a gas, is a key factor in both effusion and diffusion rates, and this is seen in everyday life where a smell like that of cooking or a smell from a perfume quickly permeates through a room. Now, finally, the rate of effusion can also be expressed in terms of the change in amount or volume of a gas over a change in time, and this simplifies the quantitative analysis of effusion in a lot of practical scenarios. Now, the super important equation that you should commit to memory for the MCAT is this one right here. Let's go ahead and apply it in a practice problem. This example says oxygen molecules travel at an average speed approximately 500 meters per second at a given temperature. Calculate the average speed of hydrogen molecules at the same temperature. Now here we're going to use Graham's law because it relates the rates of effusion for two different gases to their molar masses. Now we have the effusion rate for oxygen gas that is equal to 500 meters per second. We can also calculate the molar mass for oxygen gas that's equal to 32 grams per mole, and the molar mass for hydrogen gas, which is equal to 2 grams per mole. Now we have 3 out of the 4 variables. We can solve for the average speed of hydrogen by solving for R2 here, considering the 1 relates to oxygen, the 2 relates to hydrogen. So if we are solving for R2, we can rewrite our expression so that R2 is equal to R1 multiplied by the square root of M1 over M2. And we can just go ahead and plug in these values. R1 is 500 meters per second. Square root of the molar mass for oxygen, 32 grams per mole, divided by the molar mass of hydrogen gas, which is 2 grams per mole. Now, 32 divided by 2 is 16, and the square root of 16 is 4. So what we have left is 500 meters per second squared multiplied by 4, and this gives us 2,000 meters per second. The average speed of hydrogen molecules at the same temperature is 2,000 meters per second. Now, we can move on to our last and final objective. So far, we've talked about ideal gases and the ideal gas law. We've said that the ideal gas law is a fundamental principle in thermodynamics that describes the behavior of gases under most common conditions. It also provides a comprehensive relationship between pressure, volume, temperature, and the amount of gas, and it's expressed as PV equals nRT. Now, throughout our discussion of the laws and theories that describe and explain the behaviors of gases, we have stressed that the fundamental assumption here is that the gas behaves ideally. However, our world is not one of ideal gases, but rather real ones. And real gases have particles that occupy non-negligible volumes and that interact with each other in measurable ways. So then we ask, how do ideal and real gases compare? Well, we can start by talking about ideal gases and ideal gas particles having no volume and no interactions between particles. In addition, their collisions are elastic. But on the contrary, real gas particles have volume and they have intermolecular interactions. In addition, energy is lost during collisions. Now, in general, the ideal gas law is a good approximation of the behavior of real gases, but all real gases deviate from ideal gas behavior to some extent, particularly when the gas atoms or molecules are forced into close proximity under high pressure or at low temperature. Now we can restate this in a different way. We can say that real gases, they behave like ideal gases when? At high temperature and low pressure. And when do they not behave like ideal gases? At high pressure or at low temperature. So let's talk about these deviations. Let's conceptually work through deviations due to pressure and deviations due to temperature. So our first point is that real gases deviate from ideal gas behavior at high pressure. Why? Well, as the pressure of a gas increases, the particles are pushed closer and closer together. At high pressures, the volume of these particles becomes significant compared to the total volume of the gas. And this is because under high pressures, the gas particles are squeezed much closer together, which means that the space they occupy cannot be ignored. This causes the actual volume of the gas to be less than that is predicted by the ideal gas law. Now, real gases deviate from ideal gas behavior also at low temperature. Why? At lower temperatures, particles move slower since they have less kinetic energy. This slower movement allows the attractive forces between molecules to have a more pronounced effect. In other words, the particles spend more time in close proximity to each other, and this allows for intermolecular attractions to pull them together. This deviation due to intermolecular forces is not accounted for in the ideal gas law. With that being said, there are several gas equations that attempt to correct for the deviations from ideality, and that occur when a gas does not closely follow the ideal gas law. The van der Waals equation of state is one such equation, and it's written right here. Now we notice that there is a term that's added to pressure and a term that's subtracted from volume. That's what's different here from the ideal gas law. Remember, ideal gas law is PV equals nRT. This van der Waals equation of state is a little different because it has this added term to pressure and this subtracted term from volume. Let's talk about this a little more. Now these A and B terms, these are physical constants experimentally determined for each gas. Now the A term corrects for the attractive forces between molecules, and as such, it's going to be smaller for gases that are small and less polarizable, and it's going to be larger for gases that are larger and more polarizable. Then the B term, this corrects for the volume of the molecules themselves. Larger molecules have larger values of B. All right, now to summarize, an ideal gas is a gas that obeys the ideal gas law. Whenever a gas does not obey the ideal gas law, we say that it deviates from ideal behavior. all real gases deviate from ideal behavior, but those deviations from ideal behavior are especially significant under conditions of low temperature and high pressure. This van der Waals equation, this is an attempt to modify the ideal gas law in such a way as to account for deviations from ideal behavior. Now, this is usually covered in more detail if you ever take a physical chemistry class, but as far as we need to know for the MCAT, this is good. Know the equation, be familiar with what these extra terms do in terms of modifying the ideal gas law to be more applicable for real gases. And with that, we've covered everything we need to know for this chapter. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.